Hello everyone, today we're going to talk about how to find the expectation values of x, x squared, and the Hamiltonian for a particle in the harmonic oscillator potential. First we have the expectation value for x. The expectation value for x equals to the integral from negative infinity to positive infinity of psi n complex conjugate times x times psi n. Notice here, since the particle is in a harmonic oscillator potential, we can write x as a function of the ladder operators, x equal to square root of h bar over 2 omega times a plus plus a minus. This is because we define the ladder operators as 1 over square root of 2 h bar and omega minus plus ip plus mass omega times x, and we're taking the sum of the two, a plus plus a minus, we have 1 over square root of 2 h bar m omega times 2 m omega x. The ip part just cancels out because 1 is minus, 1 is plus, and we end up with square root of 2 m omega over square root of h bar times x, which is just giving us x equal to square root of h bar over 2 m omega times a plus plus a minus. We simply substitute that in place of x in the original integral we have, and we can distribute psi n over the parentheses to get h plus operating on psi n and a minus operating on psi n. And we can also take the square root of h bar over 2 m omega out since it's a constant. And we can further distribute psi n into the parentheses to get psi n times the rising operator operating on psi n and psi n times the lowering operator operating on psi n. And we practically have two integrals at this point, and since it's just the sum of the two. We know that when the rising operator operating on a wave function, we simply have the square root of m plus 1 times the function of m plus 1, or the next level function. And when the lowering operator operating on a function, we have square root of m, or the original coefficient, times the function that's one level lower, which is psi n minus 1 in this case. And we can substitute those two results in place of a plus times psi n and a minus times psi n. And we have our new integral as that. And we can take out the constants out just to simplify the calculation. And we have very simple integrals at this time. It's just this the product of two wave function, and taking integrals from minus infinity to infinity. Since the wave function is orthonormal, we know that when the two coefficients are equal, we end up with a 1 for the wave function. When the two coefficients are not equal, we end up with 0. So we can conclude that the expectation value of x equals to square root of h bar times m1 over 2 m omega, f n equals to m plus 1. So this part of the integral will be 1, and this part of the integral will be 0, and it just cancels out. And fn equals to m minus 1. This part of the integral will be 1, and this part of the integral will be 0, and the square root of m plus 1 simply cancels out. and if otherwise, none of those two integrals are 1, and so both of them are 0, so the whole function equals to 0. Notice here we have mass as a bold case, and the coefficient m in italic from 1 to 3 to infinity, and n is also from 0, 1 to 3 to infinity. Sorry, m from 0, 1 to 3 to infinity. For expectation value of x squared, we simply use the same strategy to substitute x with a function of the letter operators. X equal to square root of h bar over 2m omega times a plus plus a minus. So notice here, instead of x, we have x squared, so we basically square the whole thing and get h bar over 2m omega times a plus plus a minus squared. And we can take the h bar over 2m omega to the front since it's a constant, and we multiply out every part of that square and get a plus square plus a plus times a minus times a plus a minus square. Then we can distribute psi m into the sum, and we get a plus square operating on psi m, a plus times a minus operating on psi m, and a plus times a minus times a plus operating on psi m, and a minus square operating on psi m. For each part, we can calculate its value. Since a plus square is just raising the function twice, we have square root of n plus 2 times n plus 1 times psi of n plus 2. And a plus times a minus operating on psi square is lowering it first and then rising it. So we have n times psi m, which is the original wave function. A minus times a plus operating on psi m, we have it raised first and lowered later, so we have n plus 1 times psi m. And a minus square times psi m, we have a square root of n times n minus 1 times psi n minus 2. It's been lowered twice. So same as the first problem, for each function or for each integral to be evaluated as 1, we need to have them to have the same coefficients, since the wave function here is orthonormal, and therefore if n equals to n plus 2, we have this part of the integral being 1, and we can pull the square root of m plus 1 times n plus 2 out, and we evaluate the function as h bar over 2n omega times square root of n plus 1 times n plus 2. And similarly, if we have n equals to n minus 2, we have h bar over 2m omega times square root of m times n minus 1. If n equal to m, we have two part of the integral in 1, and we just adding them up. One is m, the other is m plus 1. So we have h bar over 2m omega times 2n plus 1. And we got 0 if none of them is true. For the Hamiltonian, we use the same strategy but a different identity. We have the Hamiltonian equals to h bar omega times a plus times a minus plus a half, and we substitute that in place of the Hamiltonian, and we have our new integral with h bar times a plus times a minus plus a half, and we do a simple algebra taking the h bar times omega part to the front, and we have we can distribute psi m into the sum, and we have a plus times a minus operating on some m, and 1 over 2 times I m. And we can further distribute it into two different integrals. One with a plus times a minus operating on psi m. There's one is basically psi n times 1 over 2 times psi m. And we know that a plus times a minus times psi m equals to m times psi m from the previous problem. We'll simply substitute that in place of a plus times a minus operating on psi m, and we have h bar times omega times the two integrals. So notice f n equal to m here, the whole integral will be evaluated to 1, and we have the final answer being h bar times omega times m plus 1 over 2. Fn is not equal to m due to the orthogonality of the wave functions. The whole integral will evaluate to 0, and the final answer will be 0. That's all about how to find expectation values of x, x squared, and the Hamiltonian in a harmonic oscillator potential. Thank you very much.